My name is Junseong Kim, and I'm from Seoul National University. In this talk, I will present UC check, characterizing micro-operation caches in x86 processors and analyzing its security and performance implications. This work is done with my co-workers and my advisor, Professor Jang-woo Kim. First of all, I'll describe the front-end microarchitecture of modern x86 processors. The modern x86 processor translates CISC-style x86 instructions to RISC-style microops because RISC pipelines are more efficient than CISC pipelines. Then, the decoded microops are sent to the microop queue and dispatched to backend later. Here, the most important thing is that the x86 decode logic incurs significantly high translation overhead. To avoid this high decoding overhead, modern x86 processors adopt microop cache, a dedicated cache for decoded microops. With microop cache, we can bypass the expensive x86 decoding logic. For example, if the microop cache hit occurs, the cached microops are directly sent to the microop queue without taking the decoding logic. By doing so, the microop cache can significantly reduce the decoding overhead. However, different from the typical CPU caches, the microop cache's details are not disclosed to the public. Therefore, it is difficult to understand the microop cache's internal architecture. Before describing the microop cache's internal details, I will introduce the security and performance issues in CPU caches. First, typical CPU caches, for example L1, L2, L3 caches, are vulnerable to various cache size channel attacks. The attackers can steal sensitive information through CPU caches. In addition to security issue, CPU caches are basically shared resources, therefore they suffer from severe cache contention. To analyze these security and performance issues in CPU caches, we have to understand their microarchitecture details. However, as I explained earlier, microop cache is basically black box system. Therefore, to analyze its security and performance implications, we propose UC check to extract the microop cache's hidden details and analyze its security and performance implications. Now I will introduce the background before moving on to our framework. Here is the overview of the microop cache. First, the x86 instructions are chunked as a window, and each window is mapped to a specific microop cache set. Here, the important thing is that each microop cache entry can store the limited number of microops per each entry. If the number of microops exceeds this threshold, they are spanned to multiple ways in the same cache set. Also, there is a replacement policy to deal with the cache eviction. Lastly, there is a sharing policy to handle the contention between the collocated SMT threads. As these hardware features are undocumented and different from each processor, we need a novel methodology to extract these hidden details. From now on, we propose UC check to extract the hidden features in microop caches. To extract the aforementioned 5 hidden features, we first build the diagnosis dependency map to know which feature should be extracted first. By doing so, UC check can systematically extract the hidden features on any types of x86 processors, for example Intel and AMD. For each feature, we use carefully designed diagnosis code snippets to extract its details. The first feature is the window size. As I mentioned earlier, the x86 instructions are chunked as a window, and each window is mapped to a specific microop cache set. To identify the window size, we carefully design the diagnosis code snippet as shown in the left figure. It consists of multiple chains of aligned code chunks, and each chunk has only one jump instruction. Then, we execute the diagnosis code snippet by changing the number of chunks n for different chunk size A. Here, we can figure out the window size by finding the maximum chunk size among cases with the largest dropping point. In this example, we can conclude that AMD Gen 3 and Intel Gen 6 have the window size as 64 and 32 respectively. The second feature is the micro count, the maximum number of micro-ops per each micro-cache entry. For each window, if the number of micro-ops exceeds this threshold, they are stored into multiple ways in the same cache set. The left figure illustrates the diagnosis code snippet for the micro count. The code is basically similar to the previous one, and the only difference is that each chunk consists of multiple NUB instructions followed by a jump instruction. Then, we execute this diagnosis code by changing the number of chunks n for different number of per chunk instructions u. Here, we can figure out the micro count by finding the maximum chunk size among each cases with the largest dropping point. In this example, we can conclude that AMD Gen 3 and Intel Gen 6 have the micro count as 8 and 6 respectively. The third feature is the set-way mapping policy. In typical caches, there are two types of set-way mapping. One is linear mapping and another is hash mapping. We first assume the microcache has the linear mapping, and if the extraction is failed, then we will use more complex approach. The left figure illustrates how our code snippet works. In this case, the chunk size and the number of code chunks are configured by the given set and way sizes. Here, as you can see, the chunk size is a multiple of the window size that we extracted from the previous step. Then, we execute this diagnosis code for all possible combinations of target set and way sizes. Here, we can figure out the actual set and way sizes by finding the point with the smallest set and way sizes among cases where the hit ratio has decreased. In this example, we can conclude that microcache has 32 sets and 8 ways. Next, I will show how to identify the replacement policy. For simplicity, we categorize the replacement policy into two types. One is perfect LLU and another is pseudo LLU. We plan to extend the usage check to support more complicated replacement policies as a future work. As shown in the left figure, we used a similar code snippet used to identify the set-way mapping policy. The only difference is that we fixed the set size as the extracted set size from the previous step. Then, we execute this diagnosis code for different way sizes. Here, for perfect LLU, all instructions cause capacity misses when the number of chunks is larger than the way size. Otherwise, for pseudo LLU, the cache miss ratio gradually increases. In this example, we can conclude that AMD Gen 3 has a perfect LLU policy and Intel Gen 6 has pseudo LLU policy. Lastly, I will explain how to identify the sharing policy. In typical caches, there are two types of sharing policy. One is competitively shared policy, and another is statically partitioned policy. As shown in the left figure, we used a similar code snippet used in the previous step. The only difference is that we used two same diagnosis code snippets and measured the microcache hit ratio for each case. We simultaneously execute two code snippets by changing the number of chunks for each case. Here, we can figure out the sharing policy by analyzing the dropping pattern of microcache hit ratio. For competitively shared cache, the microcache hit ratio is gradually decreased. Otherwise, for statically partitioned cache, the hit ratio is suddenly dropped. In this example, we can conclude that AMD Gen 3 has the competitively shared microcache and Intel Gen 6 has the statically partitioned microcache. Now I will provide two use cases with UC check. By using the extracted features, we analyze the security and performance implications in the microcache. For security, we first propose new side channel attacks using the microcache. Then, we also provide the hardware defense technique to mitigate these attacks. For performance, we propose logical microcache allocation to reduce the cache contention effects. The first attack scenario is cross-SMT attack. As I mentioned earlier, some processors have competitively shared microcache. For those processors, we can exploit the cross-SMT attack. The key insight is that a spy thread can identify the execution sequence of co-located victim thread by monitoring specific microcache sets. For example, let's assume the victim thread executes function foo and ba according to a secret key, and each function is mapped to different microcache sets. When the function foo is executed in the victim thread, it populates certain microcache sets. Then, the spy thread monitors the specific microcache set and identifies that the function foo is executed by the victim thread. When the victim thread executes the function ba, it updates different microcache sets. In this case, the spy thread can similarly detect the function ba is executed by the victim thread. Therefore, we can extract the victim's secret key by monitoring the victim's execution behavior through the microcache. The second attack scenario is speculative execution attack. The key idea is that even the misspeculated instructions are rolled back, the corresponding microops can be still existing in the microcache. For example, when modern processors meet a branch instruction, the processors speculatively execute the next instructions from the branch predictor. During the speculative execution, the decoded microops are stored in the microcache. Here, the important thing is that when the branch misprediction is detected, the decoded microops from speculative instructions are still remaining in the microcache. By using these transient microops, similar to the Spectre attacks, the attackers can read the unauthorized memory by using the microcache as a new side channel. We used 6 x86 CPUs from Intel and AMD to evaluate the coverage of the proposed attacks. For each vendor, we choose different generations whose microarchitecture is different from each other. First, we find that all AMD CPUs are vulnerable to the cross-SMT attack, as AMD CPUs use the competitively shared microcache. Otherwise, Intel CPUs use the statically partitioned microcache, therefore, they are not vulnerable to this attack. Second, we observed that all CPUs are vulnerable to the speculative execution attack because all CPUs keep the transient microops in the microcache. In this case, to defend these two attacks, we propose a secure microcache design. I will explain our new microcache architecture in the following slides. The figure shows the baseline microcache architecture. As you can see, the basic structure is similar to typical set associative caches. Compared to the typical caches, the microcache has an accumulation buffer to hold the decoded microops to build the microcache entry. First, to prevent the cross-SMT attack, we add a simple hash function with per thread encryption key in the set indexing logic. By doing so, the spy thread cannot identify the victim's set index mapping anymore. Therefore, we can successfully defend the cross-SMT attack. Second, to prevent the speculative execution attack, we extend the accumulation buffer to defer the microcache updates until they are committed from the reorder buffer. By doing so, The microcache does not store the misspeculated microops anymore. Therefore, we can successfully defend the speculative execution attack. Here, the proposed hardware mitigation techniques have negligible performance overhead. For more detailed evaluation result, please refer to our paper. Now I will present the performance impact of the microcache. As I mentioned earlier, some x86 processors adopt the competitively shared microcache. Here, we observe that those x86 processors suffer from severe microcache contention. The figure shows the profiling result. We measure the microcache hit ratio for different configurations. Here, single means that only one application is executed, and multi means the application is concurrently executed with other applications. In this case, we use two different applications for the concurrent execution. One is non-contentious application, which has a small instruction working set size, and another is contentious application, which has a large instruction working set size. As you can see, the microcache contentious application, for example Derby in this case, incurs significantly high microcache contention. To resolve this contention problem, we propose a software-based microcache allocation. Here, we use Java Virtual Machine to show the effectiveness of the proposed technique. As you can see, Java Virtual Machine compiles the frequently used functions during runtime, and the compiled functions are randomly allocated in different microcache sets, which incurs the microcache contention. To resolve this contention problem, we modified Java Virtual Machine to allocate the compiled function into certain microcache sets by adding some padding byte in each code block. By doing so, we can logically partition the microcache into each SMT core, which can reduce the microcache contention. Now I will show the evaluation result of the logical microcache allocation technique. We used 6 Java workloads from spec JVM, and we measured the overall system throughput for each pairwise of the given workloads. Here, all results are normalized to the baseline implementation. As you can see, our logical microcache allocation is beneficial for most cases as it can reduce the microcache contention effects. I would like to conclude by summarizing main points. First, we propose usage check to extract the various microcache's hidden features by using a systematic solution. We extract these features on different CPU vendors and generations. Then, by using the extracted features, we show the microcache's security and performance implications on various x86 processors. Lastly, we have released usage check and its use cases to public. Please refer to the GitHub project link. Thank you.